Hello and welcome to the 2024 Energy Simulation Summit. I am Sandra Arias Garzon, and I'm a Master of Science student at the University of Alberta. Today, I'll share a summary of my research in the assessment of thermo-geomechanical effects on well integrity for carbon dioxide storage in the aquistore project. CCS projects, carbon capture and storage projects, involve capturing carbon dioxide emissions from various sources, such as power plants, industrial processes, and then injecting that CO2 deep underground into geological formations. Carbon capture and storage, or CCS, has been extensively researched and is built on a strong normative framework. Many demonstration projects have been launched both in Canada and around the world. The primary goal of these initiatives is to assess and confirm that CCS is an effective strategy for capturing and securely storing carbon dioxide emissions. This is crucial for reducing greenhouse gas emissions and tackling climate change. These projects also offer valuable insights into the technical, economic, and regulatory aspects of CCS, helping to increase understanding and acceptance of this technology. Ultimately, they lay the groundwork for broader implementation of CCS, supporting national and international climate policies and aiding our transition to a low-carbon economy. Today, I'll be discussing our research on the aquistore project, a prominent case study in carbon capture and storage, or CCS. The aquistore project is located near Estevan in southeast Saskatchewan, in the northern part of the Williston Basin. This basin reaches a depth of 3.4 kilometers at the project site. The carbon dioxide that is injected into this facility comes from SaskPower's Boundary Dam carbon capture facility. The CO2 is injected into a deep saline reservoir with bottom hole injection temperatures ranging between 65 and 100 degrees Celsius and bottom hole pressures ranging between 35 and 42 megapascals. One of the important features of the aquistore project is the advanced monitoring system. Both the observation well and the injection well are equipped with fiber optic distributed temperature sensing technology, or DTS. This allows the monitoring of temperatures at depths of 2.8 kilometers for the observation well and 3.1 kilometers for the injection well. In this research, we leverage data collected from the aquistore project to assess how thermo-geomechanical processes impact well integrity. But why is it important to assess thermoelastic effects in CCS projects? Well, in carbon capture and storage projects, CO2 is injected in a supercritical state. This requires maintaining a combination of high pressure and high temperature. The high pressure has to be greater than 7.4 megapascals, and the temperatures have to be above 31 degrees Celsius. However, as the CO2 expands during the injection and begins to dissolve in the surrounding brine, it can cool the nearby rock mass, a phenomenon known as the Joule-Thomson effect. We observed this thermal fluctuation in the multitemporal temperature data collected from the Distributed Temperature Sensing, or DTS, in the injection well of the aquistore project as illustrated in the image below. This image illustrates how the temperature changes with depth during a period of active injection and the 24 hours following the injection period shut in. The injection period being the line with the square markers, which progresses during 24 hours until the temperature in depth stabilizes, returning near the initial reservoir temperature, which is represented with the line with round markers. Despite our growing understanding of CCS projects, most simulations currently used remain isothermal, which fails to account for the stresses in the reservoir that arise from temperature fluctuations caused by both the injection and shut-in periods. These cyclical temperature changes can induce thermoelastic effects in the reservoir. Such effects may lead to alterations in stress and strain, potentially resulting in induced fracturing or the reopening of existing fractures. This could compromise containment and jeopardize well integrity. Now, I'll go briefly through the methodology I am using in this project. For this, I divided my work into two. On one hand, there are the tests that I have done, which help me to do a thermal characterization of my samples. And on the other hand, there is the numerical modeling, which will help understand better the complex processes in the reservoir. Now, for the laboratory testing, I needed to obtain some samples. However, there were limitations with the availability of recovered core samples from the aquistore well, especially for the geological formations we are examining in this study, which range from the Prairie Evaporite to the Winnipeg Formation. To address this, we searched for nearby wells that belong to the same geological basin. This is the Williston Basin, and from the selected wells, we obtained samples from cores belonging to these formations we're studying. In the image below, the wells used for obtaining samples are shown with the star marker, while the project area is indicated with the square at the bottom of the image. From each of these wells, we brought about 3 boxes of core, which is roughly 60 meters of core in total. And from those, we chose samples based on lithological differences in each formation, even if they were small. For some of these wells, there were laboratory tests that were performed around the time the well was being drilled. The results of these laboratory tests were useful for us to compare with what we were measuring. And for each of our samples, we knew where were they located in their well. That means we knew where they were located in relation to the formation they belonged to. And using that correlation, we projected the position of the sample in the same formation, but within the corresponding depths of the aquistore well. As you can see in the image, we have samples from each of the geological formations that we are studying. We have roughly at least one sample every 100 meters. We utilize these samples to conduct 3 laboratory tests for the thermal characterization of our materials. These tests aim to obtain the sample's thermal conductivity, porosity, and permeability. To measure the thermal conductivity, we use the C-Therm TCI, which uses the Modified Transient Plane Source method, also known as MTPS. This method involves applying a brief, constant heat pulse to the surface of the sample. And as the heat diffuses into the material, there is a rise in the surface temperature between the sensor and the sample. The sensor registers a voltage drop, which is then used to obtain the sample's thermal properties. To assess the porosity of our samples, we employed the UltraPeak 5000 gas pygnometer for measuring solid density. In this method, we place the sample in a chamber and pressurize it with helium gas. Once the pressure stabilizes, the gas in the chamber is directed to a different chamber, allowing us to calculate the volume based on the resultant pressure drop while knowing the volume of both chambers. Lastly, to measure the permeability of the samples, we are currently constructing a system for measuring steady-state gas permeability. This involves flowing pressurized nitrogen through the sample while measuring the gas flow rate, the pressure gradient, and the temperature. Then, using Darcy's law, we can calculate the permeability under steady-state conditions. Lastly, for the numerical model, we incorporate the results from our laboratory tests to define the thermal properties. We employ a 2-dimensional axisymmetric finite element approach for this simulation. It features a multitemporal coupled multiphysics analysis, allowing us to effectively model conditions from the injection well to the observation well, as well as the transition from the secondary sealing unit, which is the Prairie Evaporite Formation, to the primary sealing unit, which is the Winnipeg Formation. This results in a model geometry that features 600 meters deep and 150 meters wide. Next, I'll share some of the results we have achieved so far, along with the outcomes we aim to achieve moving forward. The images below display the laboratory results we have obtained for the thermal conductivity, specific heat capacity, thermal diffusivity, and porosity. As for the permeability test results, we will have those once the steady-state gas permeability system is fully operational. From the measured thermal properties, we can see that the thermal conductivity measured is mainly clustered between 3 and 6 watts per meter Kelvin. This indicates the samples are neither insolative, with a thermal conductivity under 1 watts per meter Kelvin, and the samples are neither conductive, with a thermal conductivity above 90 watts per meter Kelvin. As a reference, the thermal conductivity of water is just 0.65 watts per meter Kelvin, while that of the copper is 401 watts per meter Kelvin. Additionally, the thermal diffusivity obtained for all the samples is under 1 square meter per second. The samples also have a relatively high specific heat capacity, which is around 750 joules per kilogram Kelvin, while the porosity of the majority of the samples is low. However, their permeabilities are expected to vary widely, ranging from under 1 millidarcy to a few hundred millidarcies. For the numerical model, we expect to generate images similar to those shown below, which illustrate temperature behavior in the well during injection and after shut-in. These images were generated with data obtained from the aquistore well, showing the response of the formations during warm-back following a 48-hour high-rate injection period. On the left, we have an illustration of the aquistore well configuration, extending from the surface down to a depth of 3,400 meters. This diagram displays the geological formations we are studying, including the injection horizon. Additionally, you can see the DTS line, which is crucial for gathering the information presented in the following images. In this image, we analyze data from the high-rate injection period, showing pressure measurements in both the injection well and the observation well alongside the injection rate. With an increasing flow rate of approximately 2,000 tons per day, we observe a pressure difference of 3.86 megapascals in the injection well and 1.4 megapascals in the observation well. The shut-in is pointed here with the blue arrow, which is the start of the warm-back period, illustrated in the following images. The warm-back period shows how the formations gradually warm over a period of 24 hours. On this graph, on the left side, the temperature for each formation is displayed, while on the right side, we observe the temperature change rate in degrees Celsius per hour. On both sides, the data is displayed at specific time intervals, 1, 2, 3, 6, and 24 hours after shut-in. Additionally, each set of measurements is represented by a different color. The moment of shut-in is marked by this cluster of light green points, which is also the time where the temperature in the formations is at its lowest. From this point, which serves as the starting time for our data, the warm-back period begins. During this period, the total change in temperature is approximately 33 degrees Celsius across all formations. 1 hour after the shut-in, indicated by the orange dataset, we see the fastest warming rate, when the temperature is still relatively low. Additionally, as the temperature continues to rise, the warming rate decreases and becomes more uniform across different depths. However, to ensure the reliability of the results from the numerical model, it is essential to perform a history matching between our simulated data and the measured data from the well. Our objective is for the simulated data, representing temperature, bottom hole pressure, and injection rate, to closely align with the measured data from the aquistore project. We anticipate results similar to those illustrated in the image below, where the continuous lines representing the simulated data demonstrate a strong correlation with the measured data, depicted as circles in the graph. Lastly, we will use the numerical model to obtain the same types of information measured in the well, allowing for a direct comparison between both sets of data. The model will also provide insights into the thermo-geomechanical behavior of the reservoir. Following this, we will conduct a comprehensive analysis to understand and interpret this behavior during the thermal cycles. As a result, we will be able to assess the conditions within the reservoir and evaluate the potential implications for well integrity. With that, we have concluded the summary of the key aspects of my research. Thank you for your attention, and I look forward to any questions you may have.